Cool. So monads have become popular inside of programming languages for the last 20, 25 years. The first language to embrace it was Haskell. I will speak about this later. But in the meantime, a more popular, more widely used language called Scala and other languages like Scala are embracing the idea of monads. I have the distinct feeling that that actually means that monads have peaked, but we can talk about this at the end of the lecture. So today's idea is about monads. Monads have play two distinct roles in our world. For the first 30 years of research on the meaning of programming and programming languages, researchers have struggled to understand how to organize this landscape systematically. We sensed that there was something, but we couldn't quite put our fingers on it. At the same time, it turns out that programmers of a certain inclination have wished to organize their programs in certain ways and saw similarities and differences that they couldn't express. This is where monads come in. So in our world, monads come up implicitly without telling you about them, in some ways in 3 lectures. Or something like this comes up in 3 lectures. First, we had interpreters that simply used the implementation language to express how we can determine the meaning of an implemented language, a model language. And we had very simple features initially, something like the basic arithmetic of your grade school. Then we had variable declarations and variable expressions like middle school, and we added higher order functions. And then we said, we want predictability. It's very important for developers to know what happens when an error happens, a runtime error. It would be really cool to know in which order that can happen, so that we can pinpoint the fault, the symptom of the fault, not the actual logical problem, but at least we can start searching for the logical problem from that symptom. And to make this error message reporting predictable, I introduced the idea of an interpreter that explicitly orders the evaluations of subexpressions. A couple of lectures later, we exploited that ordering because we wanted to introduce effects. In particular, we wanted variables that we can change over time. And in lecture 8, we expressed the idea of changing with the meta language, with the implementation language that we had. But by showing you some non-trivial examples, I could see, and you could see yourself, that understanding mutation and changes to variables is actually much harder than people tend to think. And so I said, let's give you a second view of this idea by passing around a store. Store passing then is ordering plus passing along an explicit data structure that actually brings across how mutation to variables flows through a program execution. We did that. And then I covered something called CPS. In many people's courses, people who follow this outline, which is due to my own PhD advisor, but has been modified by myself and by PhD students of mine, and many other people, everybody actually usually presents an interpreter that is in continuation passing style. We did not. I showed you simply how to convert programs into continuation passing style and do so with a transpiler, and you wrote the transpiler. But we could have applied this continuation passing transformation to the interpreter and put stop, grab, try with, exception handlers, all this into interpreter directly. So I didn't do that at the time, so let me do this really quick. Not a big deal, you'll recognize it. I just want to put it on the map. So this is the CPS interpreter. Let's scroll up a little bit. In principle, it has the same values as the ordinary interpreter, namely numbers and function values. But we introduce an auxiliary idea, namely the idea of a continuation, which is a function from values to values. And then we change the interpreter, inner interpreter, to take not just an expression and an environment, but it also takes a continuation. Like the store passing one takes a store, this one takes a continuation. So here we are. The continuation is then used, for example, when we find an integer, we return the integer to the continuation. That's a euphemism for saying we don't actually return, we call the continuation on the number. If we have a node that has to evaluate the left and the right sub-expression in the opposite order, and then applies an operation O, what you do is you call the interpreter on the right one, A2, pass along the standard environment, but you also create a continuation that is willing to accept the value of the right expression, and then execute the rest, evaluate the rest of this node expression, which of course means evaluate a 1 in the given environment and hand along a continuation that is prepared to take the left value. And then when the left value comes in, we can return the addition, the exponentiation, the multiplication of left and right. But of course we don't return. We call the continuation that was given to us originally for the evaluation of this expression. And by doing so, we adhere to the principle we never return. We always just call another function, and we pass along functions to this inner interpreter, the accumulator interpreter, that do the right thing, that execute the rest. So our two things in the middle are coercing things, the results to numbers, so they're not just function values. We don't want to add function values, and things blow up. Of course, we could pass along this continuation here, and then use stopping, error erasing right in here, the number thingy, directly with dropping the continuation. We don't do that. It's okay. That's the rough idea of continuation passing. What I get out of that is that grab is a one-liner. Well, roughly a one-liner. Again, you have grab that grabs the current k and binds it to x in the evaluation of bottom. We don't have mutable variables, so we just stick the continuation into the environment. That means we add x to the environment, and the value you bind to it is a conversion of the continuation to an actual value. And values in our world have to always take continuation. Functions in our world take continuation. Show you that. The original function application just took the function representation and argument value. This one also takes the continuation, because functions need to return, meaning call the continuation of the function call site. This k is the function call site continuation, the rest of the computation in the function call site. But when you have that, then you unload the function value representation, interpret the body of the function, add the parameter to the environment, and pass along the k. And we can do the same thing if you represent continuation values as lambdas that take an argument, a continuation that they throw away, and go back to the old grab continuation. That's what we do here. So if we get a procedure, we know it has this shape. That means it takes the argument value, and then takes the confirmation and throws this particular k away. That's what the underline says, and instead goes k of x. I'm passing along the continuation for this continuation here for uniformity reasons, so that if we wish to, we could merge the representation of these things with these things, but also for what we do later in the lecture. So this is a CPS interpreter, and I'm going to scroll down and focus on 3 different things from these 3 interpreters that should be the same, but aren't. Okay. Before I go on, let me ask you, are there any questions on the continuation interpreter? No questions. That seems to be reasonably clear. So in that case, let's look at the evaluation of node.
I'm sorry, before you go on, could you just go over that last function again?
Scroll up. Okay. Yeah. This one?
The fun apply.
Okay. The function application always executes the function call at a function call site. It interprets a function as it is represented, as it is applied to an argument value. Okay? In a world where you represent the rest of the computation, you also have a continuation that represents what has to be done, what has to be executed after the function call is done. Because we do not return from anything ever, but we always continue to call functions, continuation, we need to pass along this continuation, the rest of the computation at the function call site, to the function interpretation. But this k flows in here so that when we're done with the function body, we know how to return the value of the function to the site where the function was called. Okay? That's the first part. But we also have a new kind of value now, graph, injected into our world of values, a continuation converted to value. So we give const to value, this funny function name here, a continuation, and we get the actual value back. Let's look at that function. What that function does is it takes the continuation as given by graph, and it returns a funny lambda expression. That funny lambda expression takes an argument value first, and then a continuation. But it doesn't do, and the underline here is the name of the argument, and I use underline as a convention that says, I don't use this argument, I will throw it away. Okay? So instead, I will call, that means I will return the value of x to the k that was given to me at this point when I grab the configuration. So values like this one may show up also when we apply functions, because function grab continuation act like functions. If we were to represent functions directly as lambdas in my racket or in your implementation language, these two clauses would be the same. And what you would do is you would hand along, you would apply the function to the argument value and the continuation like this. And that's why I wrote this in this funny way. But it's also helpful later on for what we do in the rest of the lecture. Is that a bit better?
Yeah, seeing it again, I think helped.
Let's look at an example. Let me switch to Dr. Racket. think I have to increase the font. Is this readable?
So we see the whole screen now. It's a little bit small. The record is small.
Okay, I'll change the sharing to just off the record. Is this better?
Yeah, that's good.
Okay. Josh, can you read it?
You can make it a little bit larger.
Still larger.
Yeah.
This is huge in my eyes. Okay. So let's take a look at graph. This is a very, let me look at a simple example. In this example, you run a computation that adds 42 to the result of the sub-expression. The sub-expression says, oh, let's grab the confirmation and call it X. So somebody tell me, what is the rest of the computation once you have the value of this highlighted expression? What is the rest of the computation? Oops. Yes, you may answer, Suzanne.
Is adding 42 to
Add 42, exactly, add 42 to the highlighted expression. So if the value were 2, you have to add 42. If it's 17, you have to add 42. If it is a function, you have to blow up. All right? So let's see what the expression does. This expression grabs the confirmation as a function, and we can actually express add 42 as a function. It's it's fun x note plus 42x. So that function, in a sense, is converted into an internal value that is bound to the variable x for this sub-expression. But of course, you could flow out from there. In the sub-expression, we add the result of calling x on 1 to 2. So x are continuations that can be called just like in the assignment. It's actually exactly the length of the assignment. And by calling this function here, we jump back to this point and ignore what sits around that call. So calling x means throw away the rest of the computation, use the one that we bound to, that we stored in the environment for x. So we jump out with a 1. As Suzanne said, the rest of the computation is this. So we put the 1 in this context here. We add 1 to 42 and get 43. That's why this test succeeds. Here's a slightly more complicated one. Let's look at this whole thing. What I'm doing here, is making sure that higher order confirmations that I'm passing around, are going to work. So I'm simply returning the confirmation that I'm grabbing here to the place where I'm grabbing it. So now I no longer have a name for that value, but that value is in this position. It came right out here. Okay, so in this particular case, I'm calling a function that immediately names this value k. So I have a name again for this value. And then inside the function, I will make a decision and say, if this k is a 0, what a dumb idea. How could it possibly be 0, right? Then I call x, the escape confirmation from before, and give it 66. Otherwise, I just call k. Because I'm hoping that it's not 0, it's a value I can call. This is a truly strange expression. And we have to watch out what happens. So initially, when we call this function, clearly this k here that we grabbed, that came out of this expression here, flows into this function, so k is not 0. So we go to the else branch, and that means we return the k in the function position of this function call here, and we apply the 0. But what does that do? Well, remember, the k here is this k there. I'm going to stop again. How does the rest of the computation deal with the value that comes out of this expression that I'm highlighting here? What does it do? Okay, that one's a bit harder. Let's see what the 0 does, right? We know that k was called. Calling k is placing a value in this place and running all of this again. That's what confirmation grabbing does. So if we put a 0 here, k now becomes 0. If it is 0, well, then we just call x on 66. That means we ignore everything else the function wants to do and jump right here and place a 66 here. And that's why this expression goes to 66. This one's complicated. Not important that you follow exactly what's going on here. It's more important that we figure out, hey, what are the commonalities between the CPS interpreter and the other interpreters that we've seen in the past. So I'm going back to Safari, and you should be able to see Safari now. Is that correct?
Yes.
Great. Okay, so let's just say we have a sense, you guys have a bit of a sense of what the continuation interpreter might do. We're going to go back to it in a moment because I'm claiming that these three expressions that you see here have a lot in common. They are expressing the same idea. You can't see that unless you're a very sophisticated reader of programs. That is what I said initially, what bug does. Why in the world did we, as programming language people, not have the means to express this more clearly? So let's go from the middle up. Store interpreter in some ways expresses most clearly that something has to be ordered. Because you see a store coming in, you interpret the right side of the subject, the right sub-expression, in that store, and you get a new store back. Whatever effects happened here are now represented by this data structure there. And then we do the same thing again, but we pass for the left side, but we pass along the effects that we have already experienced in A2. So we're ordering with an explicit data structure flow through these expressions what's going on, because store plus plus, the representation of all effects that happen in the left side, all the assignment statements that happen on the left side here, they are represented by store plus plus. And they are used to evaluate whatever follows the expression here. Well, in a sense, there is a token like this flowing around in this world. And the token that we have is implicit. It says, when you see a sequence of expressions in most programming languages, these things are ordered. Turns out compilers actually don't follow that rule, but let's just say modern compilers don't follow that rule. But let's say they do. So right is the definition of right is evaluated first. Then the definition of left is evaluated first. Then we apply the operator to left and right and return that value to everything that happened before. So in some sense, there is a token going that says, when I've reached this, go. When I've reached this, then you go. And then the token then flows on and says, you go. So there's a little implicit token that says, let's force an order in here. In some ways, the continuation interpreter does this more explicitly. And I've talked about this already. Let me go through this one more time now with this idea in mind that these three pieces would express very, very similar ideas, the same idea in some ways. Here, we reach this point, and we have an explicit representation now of what's left to do. And the interpreter has to take an explicit representation of what's left to do when you're done with evaluating A2. Well, the original thing is K, but we have more to do just to get this sub-expression evaluated before we return a value to K. So we say we can interpret A2, and there's a dependency now, an explicit dependency that says lambda. And in some ways, you want to read this lambda as assign the value of interpret A2nth to the variable right 0. So this is almost assembly language now telling you in what order to proceed instruction-wise. And again, when you do interpret A1, you know that you're inside, you're depending on the result of A2 already assigned to right 0. You're going to assign A1's result to left 0, and then you're ready to perform this instruction in the arithmetic unit, in the ALU, that says add left and right register. And of course, we don't return. We push it on this, we put it somewhere so that the rest of the computation knows how to go. And in our functional world of expressing these things, we call the combination. So all these three snippets bring across the same ideas using different means of language expressibility. And it turns out we struggle to say that because for 30 years, all of us want to build interpreters that look the same for ideas that are the same, and that look different for things that are different. And we could then somebody, a guy called Eugenio Maggi, Italian, in Genoa, studying under Gordon Plotkin in Scotland, discovered a mathematical idea that allowed us to do exactly that. This is, in some sense, an incredible coincidence. Some of you may have read up on physics and how physics discovered many ideas that we now take for granted, many mathematical ideas that we now take for granted. Physics drove Newton to figure out good calculations on infinitesimal small values. Leibniz is probably the only well-known person who, contemporary to Newton, discovered the same idea just by wanting to think. But usually people have an application in mind. Newton had the apple in mind that fell on his head. That's the story, but it's not true, of course. And in the same sense, 100 years ago, we wanted to understand quantum physics and relativity, general and special. And we needed new forms of mathematics to express this more clearly. And in that way, computer science has looked to drive its development, programming languages in particular. And the first big idea was the connection to category theory that came about in the 70s and the 80s. And Eugenio actually discovered how we could capture these ideas that I just talked about, these commonalities, with something called a monad. Monad is a mathematical thing, whatever that word thing means here, but that's the best way I can say it now. And what it really says is, I am the commonality of many mathematical structures. I don't want to dive into mathematics because very few of you have taken enough math to see how topology, geometric algebra, algebraic geometry, analysis hang together with structure like that. So I'm going to give you a programmer's viewpoint of monads for now. The first thing is there's something about types in monads. We'll get back to that in a little while. But a monad is really a type transformer that hides that we have to add new things to the inputs or the outputs of interpreters. So you say monad of value, and you're done. Still there? Am I live still?
Yes, you are.
Okay, good. Because my machine freezes. So as I said to the beginning, when only 3 or 4 people were there, my machine may die, in which case I have to reboot because I unfortunately installed Mac Security Update 2020-002. Don't do it. Go look at the chat channel. So the 3 functions that you get in addition that are really important, there are only 3 functions, are triples, is a function called run, a function called return, and a function called bind. What do they do? Well, what do monads do? Monads separate the idea of a value, what we call a value, from the idea of computing with a value. So run can take in a representation of a computation that determines a value of type T, and returns it. It extracts that value. It somehow runs it. Get back to what that really means when we see the biased interpreters. But of course, you also need the idea of returning. That means the opposite of running, namely injecting a value that you have into a computation so that you can the computation can be triggered. So think of this as this is a computation that is waiting for a value, and the return thing injects that value so this thing can run. This is the opposite. I have a computation, and I want to force out the value so I can show you the use of this value. The third one looks complicated. And what it really does, what it represents in some ways, is the semicolon of programming languages. If I give you 2 monads, 2 computations, I can order them, I can sequence them. So if I order 2 of those guys, I get a third one back. But there clearly must be a connection between the first monad and the second monad. So we don't actually give you 2 monads, we give you a function that waits for the result of that one here, and then constructs this computation, this representation of a computation. Okay. So a monad for ordering interpreters, a monad for store passing, a monad for continuation passing will not implement these things the same way. But the interface of these 3 modules will look the same. Okay? That's important to keep in mind. So if you get those functions for the 3 monads, you can actually express these ideas of ordering the node sub-expression in a very, very cool way. Let me scroll. Take a look.
There is a question.
I see you, Nathaniel. Just let people look at these three pieces, and then we talk. Do you see a difference? Well, let me talk to Nathaniel now. What's the question?
Why is the type of that weird arrowish function thing? Why is it T arrow monad T in the middle there? And why isn't it monad T arrow monad T if we're kind of in the middle of the computation?
Right. Great question. I will explain it first. I will answer this twice. I will explain it again up here, abstractly. Then I will evaluate. I will explain it below in these three snippets that you saw concretely. Okay? And then I go back to you. So we want to compose two computations. Imagine a computation like x equals 1, semicolon, x equals x plus 1. So each computation is represented by a monad. And we want to bind, we can compose those two, it's pronounced bind. We want to compose those two computations, but they're not completely independent, right? X equals 1, semicolon, x equals x plus 1 actually connects by a store that has been modified at one position, the location for x. So we have to connect that monad here to that monad there by saying something flows from here to there. We express this in mathematics and in programming by saying this is not a monad, but a function that takes a value, namely the thing that we want to communicate from here, and constructs this new computation, which of course then will be the result of this thing. Okay? That's the abstract explanation. So we are composing two computations by channeling information from here to there, which is some data structure. Information is always represented as a data structure. So we're channeling this information that has to flow from here to there by a function, by dependency. Functions express dependency. If anybody who gets to high school needs to understand one thing from mathematics, is the idea of function depending and independent variables. And this is how we express flow. So let me show you with the use and then with implementation of bind, right, how that works. So here we have a computation, same one everywhere. You notice that the three computations are now the same. You have a computation that has to be composed with another computation, namely this computation down here. But the value of this expression of A2 has to be communicated to this computation. So the way we do that, we give it a function that takes the value of this thing and runs it through the rest of the computation. So composing this monad with this monad injection gives us the CPS thingy. Now, the CPS, it looks almost the same, except that we write return here. We don't actually write call a continuation. You don't even see a continuation. Let's look at the same thing again with stores, because that makes it even cooler. In the old node implementation, we saw store floating around all the time. But nothing happened to the store really inside. Only maybe the evaluation of A2, maybe the evaluation of A1 caused a change to the store, but we didn't see that. The store wasn't touched. It was just used as a data structure that flows along and orders the computation. You don't see the store here at all. What you see is that somehow there's a value being computed. That value is communicated to that thing and injected. What does the monad do then? The monad will secretly, behind your back, so to speak, also pass along the store. And you don't have to think about it. And here the monad will pass along the confirmation. And when we return the value from this computation, in this case, the monad implementation needs to somehow pass along the store so that the context gets the store. And here it needs to pass along the confirmation. It needs to use the confirmation to pass along the result value. Nathaniel, does bind make a little bit more sense?
I'm kind of mid-think here, but I guess so.
I'll give you a bit more time, everybody a bit more time to think, because this is not a non-trivial thing. Many people rearrange monads these days to look much more like conventional programming syntax, but then you question, why are you doing that? You see things that kind of look like assignment things, that kind of look like sequencing thingies. You don't really understand what you're doing, what you're actually teasing out. So I give you a moment, I give everybody a moment to think about these three snippets and think about how you might implement this bind operation and the return operation in maybe the last two snippets. Oh, I'm so sorry. With Aku is my name for interpret. I forgot to change this when I wrote the lecture. So this is just a call to the interpreter. This is interpret, this is interpret, this is interpret. Does that make more sense, Julia?
So is it the same interpreter or are they all different? So what's different between those three examples? Clearly when you have, yeah.
There is no difference. They are the same. You can write down the same text, but of course, depending on the implementation of bind and return, they will behave differently. So the trick is we use the same API, we use the same, I'm going to use Java terms, makes it easier. I'm going to use the same interface, but I have different implementations for the same interface.
So are those implementations for monad interface or also for the interpreter? Or is the interpreter the same everywhere and just...
The interpreter is the same everywhere. Gotcha. The interpreter is the same everywhere. Well, the text of the interpreter is the same everywhere. Yeah, we'll look at that in more detail. Okay, so it should surprise you, and that's why I think this first glimpse at monads, when people see that and what I'm going to show you next, they get fascinated, and it is a discovery that has slowly made it into the broader world of developers. That's why we see many more attempts at injecting monads into other languages. Let me scroll and show you what else you can do if you allow the interface to be wider than the three functions. Okay? So we have only three functions here. I don't even use run. Okay. So let's look at grab again. Grab can be reformulated when you have an interpreter by a monad-based interpreter, by allowing the implementation of the monad to hand out one more function. And this function will take this grab star function, will take a function that absorbs a continuation value, binds it to the X in the environment, and then runs the interpreter on the body. Not very different from before, but it is different. The store is more interesting and much more complex. Suppose you want mutable variables. That means your declarations no longer bind functions to X or integers, but mutable variables. Well, so now your implementation of the store monad, as opposed to the combination monad, may provide a function called alloc star. And it may provide a function called update. Here. And it may provide a function called retrieve. And these things are not implemented as ordinary things, but they know how to tap the representation of a computation to manipulate it in non-standard ways. Not the way return does it, not the way bind does. Okay, so that's just a glimpse at what you can do in addition if you widen the interface for specific monads. And that's where interpreters will differ. So before I dive in now, let me remind you, monads are there to bring out the commonalities among different interpreters and emphasize the differences. Okay? So clearly the evaluation of node is common because we make plus, times, and exponentiation not to have any side effects, any real side effects. The computation of grab or the computation of declaring mutable variables is distinct. All right, let's do a very simple monad. I'm going to show you the monad first, then I'm going to show you the order interpreter, which isn't very interesting, but it's a nice exercise, it's a think exercise. What I'm going to do is I'm going to make explicit the idea of handing computations a signal that says go. If you want to order computations in an interpreter, it's like running a relay in track and field. There's a little wooden thing, maybe it's plastic these days, but it used to be wooden, that one runner hands to the next before he or she can go on the next leg of the relay. So I have this little wooden thingy, this relay wood, and it's called go. It's just a symbol. And it could actually be the word go, it doesn't matter. So how do run, return, and bind work? Well, run clearly has to say to the computation go. It gets a result and another go signal, but it doesn't care about the go signal, it just returns the result. Okay, how does return work? Remember, return takes a value and hidden information. Every one of those monad thingies, not every one, return and bind take hidden information that they pass through compositions for you on your behalf. So here, all we pass along is this go symbol. So return has this takes a value, and that's a computation. And then it waits for the go symbol. And when the go symbol arrives, it says, I can give you the result, And if you want to go, if you are a computation, if I'm returning my result to another computation, you have the right to go. But this should not be an underline, it should just be go. So you can compose run and return, and you can see that if returns next thing is a run, well, we just get the result back. So these guys really are identities. And we'll talk about this in a little bit. Now, bind is a bit more interesting. So this is the first time we see bind implemented. And maybe Nathaniel and I can talk about this again. So remember, you get a function m, you get a monad m, and you get a function that makes it monad once m has done its work. So now this binder waits for the additional hidden information that is flowing around. When this thing arrives, when the go signal arrives for the ordering monad, what you do is you start the computation m. And m will return a value and the signal for the next computation to go. Now, f's type is if you give me a value, I give you a monad. And the monad is a function that takes the additional information that we have that we pass around, the data structure that has to go around. So clearly, we call f1 val, and then we pass along the additional data structure. In this case of the ordering interpreter, the ordering monad, all we get is a go signal. Okay. Clearly, this go signal will be a store in the store case and a confirmation in the confirmation case. What's really also often hidden and becomes a bit more obvious, I should have written it differently a little bit, I should have written it lambda. There's this currying going on. We actually take the two arguments for return and bind, the obvious argument, the value, and the hidden argument that the monad needs to do its work in two stages. And that's called currying, if you remember. And often I should really write it return lambda result, lambda go. So this is how you can pass around things behind the back of the interpreter. And you only make them explicit in functions that widen the interface. I'm going to stop here, return my attention to Nathaniel. Is bind a little bit clearer
now? Yes. What is m? What is the type of m in this example, though?
The type of m is monad t.
But for any t.
So the interface is the same, but for a specific monad, we instantiate this t to. It's just a symbol we're passing along.
Right. What confuses me a little bit, does this program really do anything?
This is an API and its implementation. So I have to show you how it works, right? So this is a library, right? Does it do anything? Maybe you want to rephrase the question. Does it do anything? What do you mean by does it do anything?
I mean, you're passing around this one symbol, right? And it's not changing at all?
That's correct. So this is a finger exercise to show you how even the most primitive idea can be categorized in the spirit of everything is a monad. Julia, is that a question or no? Julia?
Sorry, run blue jeans. So I thought that big go generates a new symbol every time.
Oh, I could have put quote something there. It's just, that's a pedagogic mistake. Think of the word go there.
So you wouldn't generate new symbol every time you do something? Okay.
One symbol go is passed around all the time. That's exactly what Nathaniel said. There's a fixed symbol, and that symbol is passed around. I will fix this when I do post prep for the post preparation for the lecture.
I do get it a little bit better now.
Okay. Let me scroll down. So what you can see now, so this is the inner interpreter I called with Aku, because these things are accumulators. You don't see the symbol go at all. You don't see that the interpreter explicitly waits to be told go for the next computation. So going back to node, this is a computation. It represents the computation of A2. We represent computations in mathematics as a function that is waiting for the hidden information. The hidden information that the composition and the interpreter will supply is, hey, go. And then when it goes, it passes along the value, and in a hidden way, the symbol go to this function. This function goes. Same thing happens here again. You can see this in many places, like if will evaluate the test in the current environment, and it's waiting for, it's a computation, and this computation is waiting to be told go. And when this go arrives, it will evaluate the test and bind the value to T and hand over the data structure that is hidden behind, that is invisible in the interpreter. And then when it arrives, when it says go, we pick the right branch and evaluate it. We show you where run shows up. So all of this is now standard, but you no longer just call the interpreter, because this what I highlight here is just a computation. And computations wait to be told go. And run is the function that injects the word go, this hidden data structure that we pass along, and now the computation can run. So only when you say run do you enter the monad, and when you return, and return is the last thing to come here, you exit the monad. Okay? I'm going to scroll up a little bit. Just a second, Suzanne. So this is what run does. It takes the computation, calling it in an interpreter, and says go. Okay. Suzanne.
So in this interpreter, the thing in the monad, the go that we're passing around, is completely invisible. So for the store passing interpreter, how in places where we actually need the store for anything, I don't know, if there's a place where we need the store, how do you get it back out in the interpreter?
That's what I will show you next. And I'm glad you asked. And I didn't pay Suzanne to ask this question. It just happens that she asked it.
You just pay me for other stuff.
So actually, I rearranged the lecture this morning. So I'm going to do continuations first. But if you want, you know what? Let me scroll the stores. This is the first half of the store monad. It has the same interface as the one for ordering. But run no longer sends along the signal go to trigger a computation. What it sends along instead is the plain store. This is my name for the initial store, right? So this is a real data structure. And watch what happens when we bind. Bind runs the, run like before, bind waits for a store to come in before it can do its computation. Then it runs that monad I was given first on that hidden information that we now call store. But unlike the Go symbol, running a computation on this store that is floating around behind your back actually may change it and may create a store plus plus. So we still hand over the value that comes out to here, like the value comes out, goes to here. But now we just get an M, another monad. And the monad is waiting for a signal to go, the data structure that comes along, the hidden data structure that comes along. And that is no longer store, but the new data structure is store plus plus. Okay? So the store is clearly different. It's the same type interface, but it's a very different implementation. Let me show you the same part for the continuation one. Again, the type interface half, the top half above the line, is the same. But the continuation that will pass along, that run injects, is very different. Jack, I see a question.
For the store, Monad, could you clarify why you don't use the store for run?
Oh,
I think.
Let me scroll down. I do run injects the hidden information into the monad that it's given. So run is given a representation of a computation. A representation of a computation waits for a store. Okay? So we give it the plain store here. And run really means I'm entering the monad, and when I'm all done, I'm returning from the monad. I'm exiting the monad. I chose, in my implementation, not to show you the store. Yes. Right? I chose not to show you the store. This is my choice of implementing this. Why am I doing that? Remember, run says I'm running the computation and then I'm exiting. I'm done. I'm no longer in the capability called store. Right? That's why when I'm done, I presumably, as a user, as the outside consumer of the store monad, no longer wants to know about the store, but only the value that came from the computation. You could talk about different things, and that could be done differently. Okay, is that better, Jack?
Yeah, I think that makes sense. Thank you.
I'll show you how to use that thing in a moment. Let me go to the CPS monad. And again, you have noticed by now I'm hiding from you parts of the monad that widen the interface. We'll go there. So this is the continuation monad. The top half is the same. I'm providing the same interface. This time, I'm using continuations which are the data structure I'm passing along is a function. And I write the function explicitly as when I get the value, I compute the answer of the entire run. Okay? So answer is really just value in our world of interpreters. I just want to distinguish those two. Answer is the final thing. The monad has nothing else to do. Okay? So the implementation is very different. This one says, I have to give you a data structure that takes a value and computes more if it needs to. But run is the thing that exits the monad when it's all done. So this data structure says, I'm a function that receives the final value and it returns it to where run is called. Let's see how return works. Well, not surprising. Return takes the value, right? And then it takes this hidden information, K, and applies K to the result. So you see that every time we returned by calling K, that's now hidden in return. And of course, bind builds the continuation for you, the intermediate computation that you need. Right? So bind takes the monad, the representation of the computation, and this F, and then it waits for the hidden continuation that's passed along behind the interpreter's back. Of course, that means that M needs to receive a continuation that somehow knows about F and the old K and does the right thing. It composes, it sequences in the spirit of continuation monad these two things. Okay. So here we get this value out of M. The value is always applied to F as the first thing, and then F applied to val M waits. It waits to be given a data structure that represents what it has to do. Well, this is the monad that went first. This is the monad we created from the information flow from here to there. And the hidden information flow is this K flowing here. Okay? All right. So let me scroll down a little bit and show you an implementation that uses this. So if you look at integer, well, it has to return. Return is a function that creates something that waits for the continuation and uses it. Note we talked about, call is like note, if is like this here. If is a good one. So if runs the inner interpreter, and it gets this extra function that when you know the test value, you check out whether it's 0, it's a number, and it's 0, it's a number, and you call then and else. Let's look at run. Run is used right here. So we no longer fire up the inner interpreter. We fire it up by saying we build the computation that is supposed to evaluate the given program AE0 and the given environment NT, and it waits. This is just a computation we're not running it yet. We're running it by explicitly calling run, which gives it the continuation. So this is how the continuation gets into here without being explicit. And nowhere in the first three things, first n constructs, language constructs that we interpret, do we see a use of the continuation at all. Same for the ordering interpreter. And we will see in the store interpreter, it's the same too. So unless you want to change the meaning of a construct or add one, it just looks the same. It looks the same. The implementation of the API is so different that the actual computation is very different. So what you see here in some sense is an amazingly cool way of demonstrating what interfaces versus classes are in fundamentals too. So let's look at an extension, grab. This is what grab looks like, right? So where is grab implemented? Let's scroll up. This is what I call the widening of the interface. In addition to run, return, and bind, I will also export from this continuation monad something that allows me to grab this computation. Is the continuation. Sorry. So what you see here is that grab star wants something, a function that is willing to accept the continuation and produces a monad. And then we'll run this thing to completion. We'll run to get an answer, just like the run function itself. So grab takes the consumer, and grab star took nothing else. Yes. And grabs and so grab star took nothing else but this one function. What grab star has to create a monad, a computation, representation of computation. And that means it has to become a function that waits for the hidden implementation, the hidden data structure of the continuation that is passed around. Until now, that was passed around behind your back. Grab star will turn this thing into something that the consumer can deal with. And it actually is the same thing as before. It takes an argument value, a continuation that we throw away that was underlined before, and it calls this K that came in at that point right here. Of course, this just creates a monad, a continuation monad, as Julia points out in the chat channel. And so it is waiting for the additional data structure to be passed along. Okay, so that is how you widen an interface. You make accessible this hidden information in some way. The hidden information was K. None of these guys gave you access to K. This guy hides it in a value that you know the user of this API knows how to interpret. Okay? We could, in addition to just doing this, we could have a different representation that just says K goes right here. But then we have to work harder when we call continuations. Okay? Are there questions on how grab is done here? Okay. This is hard material. We are pushing at the boundary of what people do. Let me get back to this. Let me stop here for a moment and talk about this phenomenon of what people do. As I said during the semester, before we shut down, before we went online, programming language theory, programming language research as a field is in a funny situation. The most theoretical work, and this is true for my own work, typically takes about 20 to 30 years to make it into practical uses. Eugenio Moggi invented these, or came up with this insight that mathematical monads could be used in programming language theory in 1983 or 1984, so just before I started as a PhD student. And it is now something that people play with. You can see it's a bit more than 30 years. When I say people, I mean software developers. And if you look at the Scala world in particular, some of you are probably going to live in the Scala world. Lots of people are pushing this, and it's not clear to me why, but they do. But this is what I mean by it takes a while. Okay. So let's look at the widening of the interface in the store case. In the store case, I chose to widen the interface by giving access to allocation, retrieval from the store, and update to the store. And as before, what has to happen is alloc takes a function that is ready to take in location, but alloc of f is just a monad that needs to wait for the store to arrive so that it can compute a value in a new store. So we're waiting for this hidden data structure to shovel along. And now I'm cheating here. I'm using the old store from assignment 9 to allocate a new location, which of course lengthens the store. And then I call f on that location, and that makes a computation. It makes a computation that waits for its signal for the hidden data structure to come along. And lucky us, in this case, it comes along right away. And of course, retrieve is just like that. Retrieve star, the function I use for the monad, uses the old retrieve, gives me the value, and doesn't change the store. Update takes the location, takes the value, takes the computation, and waits. It waits for the hidden data structure, the store that's shoveled along, that's pushed along. Store arrives, that's the function. If the store arrives, we get the old value from the store. We update the store with the new value. And now we can call f, consumer of update, with the old value. And it waits. It's a computation. It waits for the data structure. We don't pass along store. We pass along store plus plus, the modified store, for things to go. So now Nathaniel, who asked before, oh, nothing happens to the symbol. Well, now you saw two data structures, continuations and stores that really change and are exploitable as they change. Let's take a look at the store monad interpreter. Again, integers just return the value. Nodes look exactly like before. Call looks like node. Functions return a function value. Return. If is exactly like before. Computes the value of the test. When that value is given, it creates a new monad, a computation representation, picking the right branch. This is a curried function. It waits for its signal to go. Wow. What did we change? In the store interpreter, I wanted to change variables. So I clearly have to change how decal works. And I have to change how string works. Because those are things that had one interpretation before, now they have a different one. So this is how monads allow us to say some things are always the same and other things are emphatically different. And of course we use, for example, in set, we use the wider interface. First we do an ordinary bind on the right-hand side computation. We get the value of the right-hand side computation to create a new monad, a new representation, by using update. An update, remember, returns the old value and, in a hidden way, the store. So this is passed along here. Sequencing is really cool too. Sequencing really shows you that bind represents literally the semicolon. We evaluate the first part. We throw away the value, and then we evaluate the second part. Well, that sounds wrong until you think about the idea that what is passed along in a hidden way is the store that was modified here, and the modified store, not the old store, gets passed into this monad here. And of course, once again, we don't just call the inner interpreter with the given program AE0 and the empty environment. That, what I highlight, just constructs computation. And that computation has to be run. That's what run does. And run injects the plain or the empty store into the computation and everything goes. And when you're all done, you exit here. Now that goes back to Jack's question. When I exit here, I'm saying I no longer use the store. That's a very powerful idea. Run signals on return, I no longer use the store. The rest of the program is free of side effects. I'll let this sink in because I'm going to go back to it later on. But that's really what's going on here. Jack, does this clarify a bit more what we do here?
Yep, definitely.
Good. There's a question from Julia.
So it's not a question really. May I say something and you will tell if that's right?
Say again?
Can I say something and you will tell if that's right?
Yeah, go for it.
So the basic monad interface just allows for sequencing. And if the interpreter only needs sequencing, then the basic interface is the only thing we need. So the very first interpreter, which doesn't have a store or continuation, can simply use basic monad. And maybe you can count, say, the number of operations using some monad, but you won't look inside during the interpretation.
Correct.
But if you need something, if the interpreter needs to mess around with the internal state, like with the store or locating variables or grep for continuations, then because the interpreter doesn't explicitly have access to this hidden state, we need to extend the interface of the monad and add these widening like allocation, retrieval operations to allow the user, the interpreter, to mess around with the internal state using this extended interface.
That's correct.
Okay.
It's correct and not quite enough. Let me add something to what Julia said. Once you start using monads, you can compare interpreters and you can say, where are they literally the same and where do they differ? So by using monads, you can really emphasize the similarities between interpreters, an interpreter for continuations, an interpreter for stores, and you can highlight the differences. Right? The differences, of course, are all those places where you use the widened interface. Okay, cool. So I'm going to do about 20 seconds of mathematics, which really means 2 minutes. I don't want to scare you, but there is math behind that. And the math comes from really traditional mathematics. When people say something is a structure, then that often means there is a set of things, there's a collection of things, there's a small number of operations on these things, and there are laws that govern these operations. Okay? You learned this in middle school. Sadly, the way we teach mathematics in many cases doesn't bring this across. Numbers, integers, are structure. But before you get to integers, as a little kid, you learn to count. Counting goes like this. 0 fingers, 1 finger, 2 fingers, 3 fingers, 4 fingers. I know 0 is not in your vocabulary at this point, but let's say this. And you see there's plus. Adding 1 is plus. Adding 2 of those numbers, I have 2 apples, you have 3 apples, together we have 5 apples, right? That's another operation. But then at some point you will say, I'm taking an apple away from you. You have 3, how many do you have now? And you're like, oh, I have only 2 left. You have 3 apples and I take 5 away from you. How many do you have left? I can't say that. So as you actually go through mathematics in K-12, you learn to build bigger structures so that operations satisfy cool laws. For some value of cool. It's not wrapping, but it's close enough. Cool means, for example, that plus and minus are opposite operations. Times and division are opposite operations. And you heard that. I know you heard this because my son is a middle school teacher at a poor district. So many of you are not from poor districts. So you have heard this before, right? And you go all the way to logarithm and exponentiations, differentiation and integration. You see these laws all the time. I'm the inverse of the other. I'm the left inverse. I'm the right inverse. Maybe you've never heard those words because you always heard inverse. But it turns out return and bind satisfy 3 of those laws. My browser is stuck. There we go. Those are 3 laws. And what these laws do, if you are a developer who likes to think about code, they help you think about composition of computations. because certain things will always be true no matter how you implement. Well, you have to show that, but once it's shown, that's what you can use as a consumer of the API, not as the builder of the API. The builder of the API, you have to validate exactly those equations. Most developers skip that step because we have explored all the monads there are, kind of. Let me scroll down a bit. What I did here for you to read if you're interested, not for you to follow me now, is I actually validate these laws for the store monad. And they're called the calculations to validate, for example, that when you return an answer to a continuation, you might as well just call, a transformer, then you might as well just call K on A. Right? That calculation actually is straightforward. It just uses the law of fundamentals 1. Fundamentals 1, students tell me, when you apply a function, you substitute the actual argument for the x, and it's all done. And that is also true for lambdas. And that's all the laws I use here. For the third equation, I use a bit more. See that here, I have a couple of comments here and here that you have to swallow hard a little bit. So let me go back to the laws for just a moment, and we're done. What does this law do? What does this law say? This law says that when I put return on the left of a composition of monads, of a binding of monads, it's an identity on these two guys. When I put return on the right, it's the identity for this guy, for M. So these are identity laws. And if you have taken abstract algebra or just group theory, and so for me, group theory was 10th grade, maybe not for you, but if you've seen anything like this is called a left and a right identity. This one is also something that you've seen before. So you've seen identity laws before. For example, adding 0 to any number gives you that number back. Multiplying any number by 1 gives you that number back. Those are identity laws. And many mathematical structures have identities for the left and the right, and they're different. And here's almost the same, but you have to actually put A into return. What does this law say? This law fundamentally says semicolons are associative. So when you say, I have 3 statements in a row, they're sequenced by semicolon, I can group the first 2 and then the third, or I can group the last 2 and then the first. The execution will be the same. And that is true in general. All sequencing works like this, if you take into account how you write sequencing in these things. So there are intuitions behind these mathematical laws that were developed for very different fields, for topology, algebraic geometry, analysis. They apply to computations. And that's a really cool coincidence, and that's great. So I have 4 or 5 minutes left, and I would like to use those to tell you why developers find monads cool and why I believe that monads are on their way out. So let's say first why monads are cool and why people go for it. I have glossed over an element of monads that doesn't play a big role in the way I've structured the course. Monads come with a function on types. If you don't have that function on types, you have to carefully spell out and reveal the implementation detail that's behind the store API, the order API, or the confirmation API. But if you have functions that transform types, you can always just write monad of numbers. And everything works out. I did allude to a very important fact, namely that run tells you you're entering a computation of a certain kind and you're exiting it. So what the advantage of a monad-oriented programming language is this. If I want to use assignments, assignable variables, in just one part of my program, but I want to use ordinary mathematical way of programming in another part because it gives me a better way of thinking about this program, then I can say on that first part of the program, run with the store. And both the word run and the type monad of store will tell you that this is the only place where you use stores. So at the same time, the second region of your program uses ordinary functional types, no type transformer, no run function anywhere. And so you know that the ordinary laws of substitution that you learned in K-12 apply to those programs. So you can separate programs, big systems, into parts that manipulate imperative data structures or control flow in a special way, and other parts that are pure. And some people believe that this is an important idea. So I just leave it at that. I think it is an important idea. I don't want to go into details because I want to get to the other half of monads that is absolutely a downside. Everybody knows it, even those people who love monads and use them now. The downside is something that we recognize immediately because mathematicians knew about this. You should have noticed that I used the ordering interpreter, and the ordering interpreter is extended to both the continuation and the store interpreter. But I don't have grab and assignable variables in one interpreter. I let this sink in. So if monads are so great and they're the fundamental building blocks of languages, the way atoms are the building blocks of physics and then molecules are the building blocks of chemistry, why can't we compose them? Well, actually the analogy that came to my head, but atoms and molecules don't compose in a straightforward manner either. For example, a protein molecule folds, which is why we are now chasing particular ways of blocking some molecules from entering our bodies, right? In the same way, you cannot really compose different kinds of effects easily. So monads, since they are simply they're new clothes for the old emperor, they're not no clothes, but they're new clothes that just make the old clothes look better. We know that they can't solve the problem of combining grab with mutable variables. So that's a real downside. You can't just compose monads you can't even compose them per se. So people have struggled with this. Researchers have struggled with that. And they've come up with some ways of doing things, but they're not elegant anymore. So there's something that researchers already know, which monads, I think in my mind, that's the reason why monads have not spread early on from languages like Haskell to other languages, because the other people knew the downsides and didn't want to invest in their favorite programming language that they used to spread ideas. So what I predict, I'm going to make a prediction now, and all predictions can be falsified in 5 years from now. So in that spirit, what is evolving, what is coming out in the meantime is something called algebraic effects. It's a hot topic in researchers who are connected to programming languages. And it's an idea that isolates, that interprets, that gives interpretation to things like store effects, continuation effects, exception handler effects, concurrency effects in different ways. It turns out, by sheer coincidence, this is something that I discovered, but I didn't know it. And 5 years later, somebody else wrote it down differently, and that's the person who called it algebraic effects. But the implementation of algebraic effects goes even further back to something I did as an advanced undergraduate, first-year PhD student, called delimited continuations. The graph gives you the entire computation, the entire rest of the computation, but you never want that. You want to cut off, you want to prune things at certain places. For example, if you grab the continuation in an operating system, you don't want to hand out something that can reach the kernel to a user layer. We'll talk about this next time. You want to delimit it at the exact border where you enter the operating system, and vice versa from user land. And so that's called a delimited continuation, and that's one of the major ideas on how to implement algebraic effects. So I point you to two papers if you're interested in this kind of stuff. At this point, we're done with Monads. It's a standalone lecture. It's a hot idea that you will encounter. You will hear those words. You should have at least seen the beginnings, the kernel, so that when you come out of this course, you can at least use the buzzword. Let me close with, are there any questions? Time to wake up. The class is over. Josh.
So this is less of a question and more of a statement. So what should I do, being that a lot of this made only half sense to me?
That is a fantastic question, because and it's actually a great question, because I expected about 1/3 of that would make sense to you. So you made more progress during this lecture than I expected. This is a non-trivial topic. So what you do is you can literally copy and paste the code that I give you here. This has always been the case, right? You guys are primarily developers, programmers, not researchers. So the way you guys, everybody here, all 14 people of 13 people that are signed in today, all of you should always think that you have an incredible medium to explore ideas in programming. Programming languages. Turn the ideas into your favorite programming language. Download my code. Play with it. Change things. And better still, transfer it into your programming language, because as you transfer, more things will click in you. So that's the best I can suit right now. So I don't know what you use as an implementation language, but you can tell the way I spoke about Java, that Java is also a medium where you can do that. Okay? Oh, Julia is asking the questions in the chat channel. If there is demand for a national and not yet another lecture, I would be more than happy to give the expressiveness lecture. So let me say it Leaf's way. I don't know whether Leaf is actually here. No. Leaf has a saying that I love. Education is the one place where people love paying a lot more to get less. And I love students who ask me for more. So as you can probably tell, I could easily spend another semester on programming language ideas without ever repeating myself. I could probably spend a couple of years on that stuff, and you would just continue to learn things. But in the spirit of making this finite, if there's a demand, send me email, and I will give this lecture on expressiveness separately. I will announce it just another Friday. Nathaniel. Let me tell you what I will do instead. I will put more links. I will put at least a link to the initial paper by Powers and Plotkin in there. And what I will also do is, I was an editor of a journal for 20 years, and I just resigned. That journal is about to bring out a special issue on algebraic effects, and you can look there. The paper called The Limited Continuations that I advertise here is something that is, if you skip over the mathy parts, if you just look at the implementation and you read the prose, is eminently accessible to anybody who has finished this course. And sorry, wrong paper, this one. And I strongly recommend you start with that particular paper, and then learn to code up other algebraic effects as people have generalized them. What people have done is really generalized this idea a lot. And that's what I call algebraic effects. So I will do that, and I'll put the links into this margin note down here. Okay? More questions? Sam?
So the monad-like interface that you presented in this lecture, how much of that is generally provided by languages that provide monads like Haskell, and how much would you have to implement yourself?
So the interface is always the same. Remember, the base interface is the same. The implementation is different. So the languages that I'm aware of certain language groups and clusters that implement monads. Most of the time, it is implemented by people outside of the implementer group. It's actually also true for Racket. There is a monad interface that Tony Garner-Jones uploaded to the web repository. So if you were to program in Scala or type Racket or TypeScript, probably, somebody somewhere has developed a monad implementation for typically the store monad, the IO monad, and most of the time a control monad, occasionally a concurrency monad, or a list monad, which has certain uses. So there are many, many monads. If you go I suspect if you go on a Wikipedia page or Wiki Haskell page or something like that, you probably find about a dozen monads that people have played around with. The ones I showed you are the major ones, but there are many more. So you have to, in your favorite language, you have to do some Googling to find the repos and the libraries that people have developed. Good question. Mitch?
I know that in some languages, you can do things like write a matcher for a monad, like I believe for the result monad in Rust, if I understand it correctly, there's like the OK version of it and then the none version of it, and then you can say, oh, if the monad is OK, then extract the result, otherwise do something else.
No.
How does that work with the monads that you described here?
Okay. So we saw Rust, and we actually, I think it was Neil and Tariq who used Rust. I don't know whether they're here, but in Rust, you can't say I have an exception. What you do is that Rust actually baked an exception monad, and just an exception monad, into the language. And it has to do with why the language exists and what it's supposed to accomplish. And so, of course, it implements in principle the idea of composing and injecting or returning and running at the same time. Except that you don't see it. It's baked into the language. So you only see it when you say, I have to construct an exception, an answer, and the answer is either okay or not okay. And not okay means there's a string that describes what went wrong. So the exception isn't raised. What does that mean? Well, you clearly have a widening of the interface that gives you three things. The first one is you can inject things into this monad. Just not the information is not just passed around. You can construct not okay, okay. Number two, you can intervene at certain places and open up the hidden information and see, is it an okay answer or is it not okay answer? And so you can make a decision on that, and that is exactly what an exception handler does. The third one, the third hidden point, is not a whiting. The third part is a run that sits implicitly at the top of the program. And so when a Rust program as a whole fails and returns a not okay, well, in the alpha version, it would then raise an exception and say, oh, I ended in an exception. And you better watch it. I don't know whether that's in modern Rust. I've given up on that. But that's the idea. So it's a standard weakening of the exception interface, but the language has baked it in, so you actually don't see bind, you don't see return. It's just there. So
gotcha. Thank you.
Rust has other monads. I'm pretty sure that Rust programmers will develop monad-like things. I will say Rust is probably a language that will have a hard time with monads, but that's just a guess. Maybe I'm wrong. Traits are very powerful. Okay, more questions? I don't see any questions. Let me remind you, if you would like to see, oops, Alex.
Yeah, so earlier in the lecture notes, you annotate that like monad of store equals and like a certain type. And I was just wondering like what that meant or indicated.
So what it tells you is what is the hidden information and how it is woven into the flow. Right? So monad doesn't tell you what's hidden. It just says, I'm a type transformer. And I don't tell you what I'm passing around behind your back. Right? And so when I annotate in my comments that, for example, the store monad is actually giving you a function that takes a store and then returns both a value and a store, I'm showing you what the hidden information is. Right? The same is true for continuations. When I say the continuation is something that we pass into the monad, and that's a function from value to value. And in the sense, in the order monad, it's a bit trivial because I just say, oh, I'll give you a symbol. Right? But these are annotations that tell you what the hidden information is that monads pass around. Does that make sense?
Yes, thank you.
Great questions. So one more time, let me remind you, if you would like another lecture, if you want me to actually give the expressiveness lecture, I would do so, and I would probably do so next Friday. Just send me email, and if there's enough email and enough interest, I will arrange for it. Okay, so they're speaking of finishing the lockup, the lockdown, whatever it's called. I feel like a locked up person. So hopefully it's over soon. In the meantime, stay healthy and stay safe. Goodbye.